మాట్లాడండి మీరేమన్నా వినిపిస్తుంది.
హలో ఎవరి వాయిస్
మాట్లాడండి మీరు మాట్లాడండి.
హలో హలో ఎవ్రీవన్ శ్వేత వచ్చింది. మిస్టర్ స్టార్ట్ అయింది కానీ ఇంకా ఎదురు చేయడానికి రెండు దగ్గర 3.2 ఏంటి?
మనకి వినిపిస్తలే కదా.
అలా కాదు 3.2 ఏంటి? టైటిల్లో అది లేదు. ఏరోస్పేస్ ఇండస్ట్రీ అంతే. ఆ 3.2 ఎక్కడి నుంచి వచ్చింది?
మీరు మాట్లాడుకుని వినిపిస్తుంది వాళ్ళకి.
ఒకటి ఏమో నాకు తెలియట్లేదు.
శ్వేత క్లాస్ చేస్తుంది. ఓకే అంటే మాకు వినిపించట్లేదు అట్లా.
ఉదయ్ సార్
ఉదయ్ సార్ అన్న చెప్తాను.
ఉదయ్ సార్
ఉదయ్ సార్ నువ్వు కూడా లాగినావు కదా.
వినిపిస్తుందా లేదా?
చూడు ఒకసారి నువ్వు కూడా మాట్లాడు ఒకసారి, మాకు వినిపిస్తుంది.
శ్రీకాంత్ సార్, కెన్ యూ హియర్ అవర్ వాయిస్?
వినిపిస్తుందా?
Is it audible? Audible?
శ్రీకాంత్ సార్.
Shrikant sir.
మాట్లాడు మేడం. ఇక్కడ కాల్ చేస్తా.
సార్కి కాల్ చేయి.
పేరు
Sateesh. So waiting for the session. చూడు మ్యూట్
Good afternoon, everyone. There's a small technical glitch at the speaker's end. We will get back by 2:15. Sir said another 5 to 10 minutes it will take for him to resolve it. So I request the participants to kindly wait for another 10 minutes. I'm audible, right?
Education is the most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. The most powerful weapon which you can use to change the world. Of believing in this principle and promoted it in 2005. Meet the man, Sri Murray Lakshman Reddy. Ushered in the silent mission. Welcome to Murray Lakshman Reddy Group of Institutions, a mission providing world-class education and research facilities to help transform people's lives for the better. Imparting education with wisdom can use to enrich the values of believing in this principle and promoted it in 2005. Succeeding the paths of Sri Murray Lakshman Reddy, making education a positive experience. Murray Lakshman Reddy, Sri Murray Rajashekhara Reddy, Murray Lakshman Reddy Secretary, nurtured MLR provides world-class education and research facilities to help transform among top engineering colleges in Telangana for the past consecutive academic years. The rich values of believing in this principle in vast and peaceful area of 35 acres. Sri Murray Lakshman Reddy tend to learn experimenting life projects through centuries. Murray Rajashekhara Reddy Skylab Secretary Institutions provides world-class education and research facilities to help transform among top engineering colleges in ultra-modern for the past academic years. The rich values of believing in this principle in vast accommodating 1,000 plus audience. Sri Murray Lakshman Reddy hostels to learn experimenting life projects through centuries. Rajashekhara Reddy Skylab Secretary Institutions provides world-class education and research facilities to help transform among top MLR institutions for the past academic years. The rich AICTE recognized MLR vast institutions accredited by NACS with A-grade measurement and has MBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR Group of Institutions with most advanced multi-sports facilities like MLR Group Badminton Coach for table tennis, billiards, and basketball, etc. MLR class institutions, MLR Sports Complex organizes national and international university level sports fairs by grooming every aspirant in MLR's national club and inaugurated by MLR Group of Institutions with most advanced and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sports persons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8+ market-ready products and supported 11+ student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25+ funded projects, 700+ SCI or Scopus Journal articles, and 35+ intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education, and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in community services (EPICS) in association with Purdue University, USA. Scope: School of Programming Practices to hone the coding and programming skills. Students' Platform for Engineering Education Development (SPEED) empowers the students to become a factor of change in engineering education and its effect on society and environment. Club Literary to organize MUN, TEDx Talks and Techno-Cultural Fest to uplift student communication and English skills to the global forum. MLR Library is fully loaded with diversified study material, books, national and international journals with dedicated digital library along online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR assures the safety and security of the students. Its transport infrastructure includes modern and secure vehicles and strictly complied with RTA regulations with well-maintained safety standards. MLR Group of Institutions having faculty of nationwide experienced and renowned adjunct professors include the expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU. Imparts education with pure practical inputs. Offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, M.Tech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now, 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education. Powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005. Meet the man, Shri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Shri Murray Lakshman Reddy, making education a positive experience. Shri Murray Rajashekhara Reddy, Founder Secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Situated in vast and peaceful area of 35 acres, students here tend to learn experimenting their live projects through centers of excellence, which is tied up with various industries. Spacious and comfortable classrooms, corridors, advanced laboratories, with equipped ultra-modern audio-visual technology auditorium, accommodating 1,000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. are salient features of MLR Group of Institutions. AICTE recognized MLR Group of Institutions accredited by NAC with A grade and has NBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR Group of Institutions with most advanced multi-sports facilities like cricket stadium, badminton court, table tennis, billiards and basketball, etc. MLR Sports Complex organizes many national and international university-level sports fests by grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sports persons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8 plus market-ready products and supported 11 plus student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25 plus funded projects, 700 plus SCI or Scopus Journal articles, and 35 plus intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in community services (EPICS) in association with Purdue University, USA. Scope: School of Programming Practices to hone the coding and programming skills. Students' Platform for Engineering Education Development, SPEED, empowers the students to become a factor of change in engineering education and its effect on society and environment. Club Literary to organize MUN, TEDx Talks and Techno-Cultural Fest to uplift student communication and English skills to the global forum. MLR Library is fully loaded with diversified study material, books, national and international journals with dedicated digital library along online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR assures the safety and security of the students. Its transport infrastructure includes modern and secure vehicles and strictly complied with RTA regulations with well-maintained safety standards. MLR Group of Institutions having faculty of nationwide experienced and renowned adjunct professors include the expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU. Imparts education with pure practical inputs. Offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, MTech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education.
Uh, Sorry for the inconvenience. We'll just wait for another 5 minutes for the speaker to join. As he's from a defense sector, he has to come out and join, so that's the issue. Internet and all, he can't use Zoom there. Kindly, I request the participants to please spare. Thank you. Am I audible? Uh, may I know who is administrator? Can you please rename yourself? Administrator.
with equipped ultra-modern audio-visual technology auditorium accommodating 1000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc.
Good afternoon, everyone. May I add audible to everyone?
Good afternoon. Good afternoon, everyone. A warm welcome to today's afternoon session. Dr. V. K. Satish completed his PhD from IIT Kanpur in 2009. Currently works scientist in Center of Societal Missions and Spatial Technologies, NAL. Satish Garu does research in space, smart materials and structures. His most recent publication in low cycle fatigue evaluation of nickel titanium cisma thin wides Further, he has also contributed to the design and fabrication of unmanned air vehicles. He has 12 research papers, 32 citations. His research interests includes composite materials, smart materials, structures. I heartily welcome Dr. V.L. Satish Garu to address the gathering.
Good afternoon, everybody.
Dr. V.L. Satish Garu.
Yeah. It's my pleasure to be with you all and share my experiences in the area of the smart materials and structures. Actually, I started my research with the smart materials, and of course, I'm continuing it as my research domain, along with the composite structures. So I wish to thank you, MLR Group institutions, for giving me this opportunity to share my experience with you all. Of course, am I audible?
Yes, sir, you are audible.
Okay, thank you very much.
Thank you. Sir, you are sharing your screen, sir?
You want me to start my talk?
Yes, sir. You can share your screen as well.
Yeah. Okay. Can you see the screen?
Yes, sir, we can see the screen.
Okay, thank you. Let's start. Actually, I would like to keep it as a more interactive section than the formal presentation. So I will be covering. I'll be covering the first initially the structures part, smart structures, then followed by the smart materials. As Madam was mentioning, I'm belongs to the Center for Societal Missions and Special Technologies. These special technologies are the various comes under various umbrella of various technologies like smart materials, autoclave, and the radome technologies, etc. And we are also doing for the societal things like um, weather radomes, wind energy program, like that. And these NAL comes under CSIR, as you all know. We basically focused on the research of related to the aerospace of all the categories like aerodynamics, airframes, flight dynamics and control, avionics and propulsion. We have world-class testing facilities here, starting from the wind tunnels to the full-scale testing of the aircrafts. Uh, as I mentioned before, we have also spin-off technologies like polymer processing equipment, wind energy, and we are also working on the coatings. So you can see that NAL has participating in all the civil as well as military aircraft programs. We have our own 18-seater, now it is 19-seater Saras Hansa. It's a 2-seater trainer, 5-seater CNM5. Along with that, we also contributed to the LCA Tejas. So Hansa is a all composite aircraft. It's a trainer category, and remaining two are the metal. We are also into the unmanned air vehicle fabrication, design, everything, testing also. So right now the Hansa fabrication is going on, of course, in our hangar. So actually, I was busy with that, so it got me delayed to, I mean, connect to the connect to the program. So thank you for waiting on. These are the our division work. Actually, as I mentioned before, we do work on airborne radomes, autoclaves, Hansa, there's a two-seat aircraft, unmanned air vehicles, ground-based radomes, and wind turbines. Uh, I think all the faculties, majorly from, I mean, most of this from the aircraft technologies, aircraft aerospace engineering background. So we know that the design drivers of the aircraft technologies are the safety, low maintenance time, less environmental footprints, and its quality of the passenger and its affordability. Initially, when the Wright brothers started the aircraft in 1903, the major aircraft structural material is the wood, muslin as the fabric, and engine basically made with the aluminum. Later, the speed and has come into the aircraft, so the material has changed to the aluminum to suit the speed and performance. Next almost till 1980, there's the aluminum is the basic structural element in the aircraft. Later, the polymer composites have been introduced into the aircraft, basically in the secondary structures. Then later they started using in the primary structures like horizontal tile, maybe some parts of the wing, etc. So what technologies we will see in the airframes basically in the future is nothing but we will going to be have a smart aircraft where that it changes configuration, it's identify its any flaws are there in the structure, etc. So if you all we call them as a smart technologies. This can be categorized as a morphing technologies, where we all know that the aircraft is designed for a specific configurations like cruise condition. But we know that when it is taking off and landing, it needs more camber in the wing, and there is certain requirements are there. So that's why we are giving the slots and flaps, etc. So these discrete uh, flaps and the slots, their efficiency of the aircraft will be reduced due to that. So we try to mark the wing itself so that the continuity of the airfoil will be maintained, and we can improve the efficiency of the fuel efficiency of the aircraft. So the next important thing is the integrated structural health monitoring. We know that there is every certain number of hours the aircraft need to be sent for the checking, and any damage or anything is there, we need to take care of it. So it will waste a lot of time. Actually, the time is money in the aircraft industry. So in order to reduce the downtime, the integrated and vehicle health management will help us in the this time downtime. So we monitor all this health, the strains or stress, whatever is required to study the its health in the during the flight itself. Once it comes back, we will try to analyze the data and try to see uh, whether the aircraft is required to address some issues with the damage or etc. So next generation polymers, these comes in the next stage. Like you identified a damage, so again you need some time for it to rectify. So whether using some kind of polymers where it can heal the damage itself in the flight condition itself. So that is the next thing that we would like to see in the future aircrafts. And The other thing is the active vibration control, and of course the noise control. This is it comes in the passenger comfort point of view. It is very important. So I'll be covering almost all these areas. So we know that as I already mentioned, that advantages of smart technologies is it will improve the performance, extend the service life, reduce the cost of operation. So we start with morphing. So the morphing has a different kinds we can expect from the performance point of view, like airfoil camber change or active twist, etc. And next is the health monitoring. So we on during flight itself, we will try to monitor its health, take the data, analyze there in the online or offline, and try to see the remedial measures. So if we do this during the flight itself, it is a self-healing. So while flight condition itself, we'll try to seal any cracks are there or delaminations are there during the special agents, and then that will also improve the actually the maintenance time. Similarly, as I mentioned, the vibration is it will the point of view of the passenger comfort will try to reduce the vibration and noise. So how can we describe a smart technology? It's almost mimics the biological functions, like how a biological thing will react to the condition. So this can be achieved by using flexible skins and with a distributor activators, sensors, and with a suitable control law and powering devices. So all these points will be inbuilt in the biological future functions of any living system, but we are trying to put that into an aircraft. So for this, we need to use the special materials, what we call them as smart materials. So let me get into that a little later. Before that, I will try to show some research related thing that we have carried out to get this morphing, all these smart technologies. So we have tried morphing can be, of course, various categories as I mentioned before. This is a wing twisting, leading edge droop, fused trailing edges, active winglets. So we have tried the active drooping of the leading edge by considering some typical aircraft leading edge portion. So we have created the weak portion where it can be drooped around. So using the shape memory alloys, we try to droop the surface. So what you can see from this figure is this surface will be remain intact, in the sense there is no gap we can see between the leading edge and the rest of the wing. Whereas if you use the flap or slot, there will be a discrete portion in between them. So we could achieve about a 10 degrees droop. That was the requirement. So this shows the time versus with the angle of the droop. So we also tried the leading edge droop for the MAV. This is a black light MAV, which is about 300 mm diameter. I mean, the airfoil will fit. It's not airfoil, actually it is basically a platform with a cambered surface. So that can fit in about 300 mm diameter. So we have tried a flight test also to this. So this could be, I can say, successful with some small problems, because being a small small, what you call small aircraft, the stability is a big issue. So it should be very, very precise, and control must be very to the dot actually. So next thing that what we have tried is the changing the active mechanism in the Hansa, which is as I mentioned as a two-seater aircraft, to a shape memory. We have rigorously tested in the wind tunnel. This figure shows the mechanism that we have adapted for that. So this the two shape memory alloy wires, and this the connecting rod which we will move this glide to activate the trim tab. This group angle we have measured using the potentiometer. This will give the feedback to the control system to activate the wire. So I'm not getting into the details of the control mechanism because it's a different topic altogether. As I was mentioned, we have done a rigorous wind tunnel test for the this SMA actuated trim tab under 25 meters per second, 35 meters per second, and 45 meters wind speed. So this trim tab angle that was set to 30 degrees to 21 degrees. In both sides we have tried that. I mean, even the elevator also in the up and down position. So this is the test setup in the IAC. We have carried out this test in the IAC. You can see the test setup. So full elevator we have shifted to the tunnel, and we have carried out all the testing. Next thing is the SHM, structural health monitoring. So we can see that today aircraft there is no onboard health monitoring system. So during the landing we need to inspect complete aircraft. Of course, it's a specific duration will be there. In that duration we need to inspect and diagnose the problems and resolve the problems. So what we can expect in the future is this inspection and diagnosis will happen during the flight, and we'll try to resolve. So the fourth point that was the self-healing materials. If you use this will be done during the flight itself. So there won't be much time for the maintenance. So this is the advantage of the health monitoring. So this integrated health monitoring can be divided into the structural part, actuator systems, and engine health monitoring. So we have also carried out some work on structural health monitoring area. We use the model-based analysis, model-based techniques to see whether how much extensive damage we can able to find out using these model methods. So there are other group in the NAM who are working on the lamp waves and optics based techniques. So we use various sensors to identify the stress and strain levels in the aircraft, like resistance strain gauge. This is a very primitive thing to the fiber optic sensors, like fiber gratings. So this is the work carried out at my place. We try to predict the delamination of GFRP beams So what extent we can able to find using the basic method like model analysis. We use the piezoelectric sensor for identifying the frequency. So we have tested with the, we have given the, we have vibrated the structure with the shaker, and 3 different locations we have considered the delamination. Basically, it is a study of the size of the delamination that we can be able to find. So 3 levels, I mean, in the sense the root region, middle region, and the tip region. We have also carried out the analysis in the abacus, and both the data you can see here in this table. If you see this is the frequencies of undamaged one. Basically, we can't find anything from the twisting mode or lead lag mode, so I have only focused on the bending modes. So the first frequency is 4.89, and from the analysis it is 4.26. We are very close. If it is 20% area, the root area is delaminated, you can see not much change in the both analysis and experiment also. So if you see the fourth mode, you can see the variation is little bit. So 146.67, what we have found is 145.1. This also, there is experiment, there is a drastic change actually. There is about 4 hertz frequency, the change is, we observed it. So, but whereas the damage goes towards the tip, it is very, very difficult. In the sense that, of course, the frequency also depend on the stiffness of the material. So where very close to the fixed end, you can see we can see the change in the frequency. Whereas if we go to the end of the about the 8th or 9th mode, you can see even the other places also we can able to detect it. So this figure shows the area of the delamination. So only one case we have considered. If suppose the delamination is at the root, so 13.3% of the total area to 6% of the total area, what is the delamination that we can able to find it out. So from this we can see that as we go the higher frequency, it is easy to find out the delamination. This is a very preliminary studies we have done with some BTech students. So my other division in the NAL, they have done the FEG. They use the FEG sensors to monitor the online strains and strain rates, basically strains, and they have monitored. They have loaded the. I think even Hansa also. Hansa, they have put the FBG sensors and try to find the strains in the aircraft. This about the different sensors, but I'm not getting into the details. So let me focus on this slide more. We have to see the small sensor which can be integrated in the structure. There should be long-term reliability. Cost should be minimal. There should be no shift in the calibration during the operation. These are the things we need to consider the sensor into the structural monitoring. But data acquisition is a biggest problem actually. So we will, every flight there will be terabytes of data will be loading into the memory. So what we need to keep and what need to destroy. That is very crucial thing. So data acquisition, storing, and managing the data, and try to figure out the what is the shift of strain or the location of the damage is very challenging thing. So it should be low weight, lightweight, and it should consume low power. It should be integrated with the avionics, and they should strains should be distributed. So the next important thing is the prognostics in the SHM. So you have the data, but how do you find out where the damage is and how extent the damage is? So that's what we try to address in our previous study. What is the extent of the damage, and where the damage is located. Next thing is the active vibration control. This is the study done by my master's student. Of course, I did my PhD in the vibration of the composite structures, active vibration. So this is the extension of the work. So we have introduced the controllers into the system. So the top will be acting as the sensor, and the bottom will act as a actuator. So we use again the preliminary control law, that is negative velocity feedback, and you can see the controlled response of the beam at the tip. This is the without the control. It is just observed what it is, and then this is the controlled one. So
Hello, sir. So your voice is not audible.
why, ma'am?
Yeah. Now
Am I
it is
audible?
okay. Now
Okay.
it's okay, sir.
Okay, thank you. So basically, we were looking for the material which can be used as a sensor and actuator together, or yeah, so that it can perform the both the operation along with the structural. It should have the structural properties. So we
Hello, sir.
the smart materials. So I will start with the shape memory alloys. I think I have some time, right? I can. Till now, any doubts or any clarifications are required? Hello?
Participants can pose the questions directly or place in the chat window.
Okay, ma'am. Let me see. I don't think. So I'll continue with the shape memory alloys. This material retain its original or parent shape during the application of a mechanical or thermal loading. So if you see a conventional material, suppose if you parent state, which is nothing but the austenite phase. Basically, it changes to the martensite phase with the lowering the temperature. So we get into the martensite phase. During the application of the mechanical loading, it will retain its the elongated shape. Once you apply the heat, it will come back to its original austenite phase. So there is a phase transitions taken place with the application of mechanical loading or the thermal loading. So if the phase transition takes place during the application of mechanical loading, it is called pseudo elastic effect, or the super elastic effect. So here the transformation takes place at the so this is the reverse transformation area. So similarly, when you lower the temperature, the austenite phase will change it to the martensite phase, and this it is in the detuned martensite phase. So detuned martensite phase, the area will be, I mean, the length or whatever is change is not much, but when you apply the load, it will elongate, and the material will retain its elongated shape. So when you apply the heat again, it comes back to the original shape. So this effect we will use, this effect will allow us to use it as a actuator. So in the activated stage, when you want to use this material as an actuator, we will take a martensitic phase shape memory alloy. So the second advantage of this material is at the room temperature, we can keep this material at the austenite phase as well as the martensite phase. So we'll keep the martensite phase at the room temperature. We elongate it, and we will get to the elongated shape. And by the application of the by heat, if you apply the heat, it will come back to its original shape. Hope you understand what I try to convey. So exothermic, and the reverse transformation is an endothermic. So it absorbs the heat and getting into the austenite phase. So in this material, there is a strong coupling between thermal and mechanical phenomena exist. So this helps us in using it as a actuator as well as sensor also. So you can see in this figure little elaboratively at the high temperature there is a cubic crystal structure will be there in that, and if you application of the if you reduce the temperature, it will form the twin martensite phase. So the shape almost will accommodate within that particular shape. If you apply the mechanical loading, it will deform and form the built-in martensite. So with the application of heat, then we'll get back into the austenite phase. These phase transformations are first order transformation. So during the transformations, heat will be regulated from austenite to martensite and taken back during the martensite to the austenite. So this will create the hysteresis in the transformation. I mean, during the transformation, we can see the hysteresis in the stress strain behavior. During some temperatures, there exists a austenite and martensite both the phases. So this you can see the first figure shows the super elastic or pseudo shape memory effect, where, as I mentioned, this room temperature it is at the austenite phase, and with the application of mechanical loading, it goes to the martensite. With the application of the reversal, it will come back to the austenite phase. Similarly, when at the high temperature, this is at the austenite phase. When you reduce it, it will come to the martensite phase, and the reverse side, it will go back to the austenite phase. We have carried out the cyclic test on these superelastic shape memory alloys, and with the different frequencies. We have also recorded the thermal signature during the loading. This figure shows the thermal signature from infrared thermographic camera. The red portion is the transformation from the austenite to the martensite, where it liberates the heat, and in the reverse cycle it will take back the heat. So this is the endothermic stage. So this is the stress strain cycle, which shows the hysteresis effect. Now we'll also introduce this shape memory polymers, where my colleagues are actively involved in. These materials, while heating at the room temperature, these materials are in glassy state. If you heat it, then it will become the rubbery state. Then we apply the loading, and we just cool it. It sets to that particular shape. Then with the application of again heating, then it will get back to its original shape. So this figure shows the complete behavior of the shape memory behavior. So you deform to the above TG. This is a glass transition temperature, where the material will transform from the glassy state to the rubbery state. Then you just hold that particular, whatever the shape you want to that shape, then cool down, then it will retain that shape. Then if you again heat back to the above the TC, then it will come back to its original shape. So this is for various temperatures and strains we have. So we're using the shape memory polymers. We try to do some tooling using the polymers. So what the shape we need is the hexagonal shape. So we make the mandrel or the tool with the hexagonal shape. Then I think it is the other way. Sorry, it is the other way. We need a circular tube. We need as a composite. So what we make is the hexagonal, so that the area of the contact is very minimal. the SM shape memory polymer. Again, it folds back to the hexagonal shape. Then we will remove the mandrel from the composite. So this is one of the uses of this material. We can also use for the morphing also, where we can use this material as skin, so that we can heat, so that it is easy to bend and it will retain its original shape. So this shows the complete cycle of the shape memory shape memory polymers usage. So let me play from the beginning. So initially it is an hexagonal. We heat it; it will become circular. Then we will lay on that. Then we cool down this thing. We heat it so that it will change its shape. Then we will remove the mandrel. So basically, making the circular composites are very, very difficult, because the releasing of the core is quite difficult thing. So there it will play a very good vital role. If you see the phase transitions in the shape memory alloys, basically it's a first order thing, where the Gibbs energy, the temperature, there is a shift in the transition part. So you can see at the rate of the Gibbs energy, that is nothing but entropy. Entropy has a discontinuity at the transition. Whereas in the shape memory polymers, it is not at the entropy, it is the next, it is a specific heat where you can see the discontinuity. It is the second order phase transitions. So I am not getting into the details of these phase transitions. Hope you understood from basically it is in the figure. So I'll be moving into the piezoelectric material. This material has a direct piezo effect, where when you apply the electric field, it will produce the pressure. So the piezo means the pressure. If you apply the electric field, when you apply the pressure, it will produce the electric field, which is the direct effect. Whereas in the indirect effect, when we apply the electric field, it produces the mechanical strains. So direct piezo effect is useful in the as a sensor. The indirect effect, piezoelectric effect, will be used as a actuator. So of course this also will change the phase transition, but at very high electric fields. So it will change from cubic to tetragonal. Effects. If you see the relation between the strain and electric field, it looks like a butterfly loop. So it changes its dipole orientation along with the electric field. So magnetic structure materials. What is the thing is, we will apply the voltage. It forms the current. It forms the current and try to elongate the material. So the initial length of this material is L. With the application of electric field, the magnetic induction, let us say in that way, so it will extend its length to that entire. So So these can be used as electromechanical transducers, sonar transducers, and automotive fuel injectors. Being these materials, we can see the more than one physical behavior, like mechanical behavior along with the thermal in the shape memory alloys, and electrical behavior along with the mechanical behavior in case of the piezoelectric material. Magnetic behavior along with the mechanical behavior in the magnetostrictive material. Similarly, the electrostrictive also, based on the electric field, if you apply, it will change its length. So it's a coupled behavior you can see in these materials. So we need to model its behavior, we need to go back to the basic fundamental thermodynamics. Start with your energy balance equation, then write back the Clausius-Duhamel inequality, then free energy, then we'll try to derive the driving force for the transformation kinetics. So finally, we will validate these models with the experimental and try to obtain those some parameters what we are used in the formulation. So I'm not getting into those details, but if you are interested, you can go through my papers. So we have done the modeling for piezoelectric material. You can go through the publication where you can see the detailed way how you model the thermomechanical behavior of the materials. So this figure shows the FBC material. So if a light will change its spectrum, so when the light spectrum will be changed with the strains. So we start with some frequency like here, and with the change of its strain or its behavior, it will be shifted. So if it is a tensile load, the shift will be at the positive side, and if it is a compressive load, the shift will be at the negative side. Based on that, we can able to find out the whether the stress strain, and based on the shift, what is the strains in the material. So in the next generation polymers, there are the self-healing materials, 3D composites, and tough and stitched composites. Basically, our focus is on the the smart materials. I will just restrict myself to the self-healing polymers, where we put some microcapsule of resin or this healing agent in the structure. So when the crack hits, this healing agent expands and try to cover the crack, the delamination domain. So that's how we expect the structure will heal by itself during the flight. We have also carried out some modeling of the 3D composites. I'm not getting into those details now. So this facility available with our sister division, advanced composite division, where they're using the tufting for improving the third dimensional properties in the composites. So this third dimensional fiber will improve the fracture toughness of the composites. So with this, I will conclude my talk. My sincere thanks to our director, Sateesh-NAL Jadhav, Ramesh is our and Dayananda is my research colleague. Presently, he is in the CSR headquarters. He was heading our division before. So Senthil Kumar was in the EC background, where he has helped us in the controls and actuations. Jaishankar is the other two, Sanjay Rao, Kavita Rao, they are in the polymer group. Nadim Masood, and they worked in the stuffing part. And majority of our work was carried out from the national programs like NPMAS, AirBeam projects. So I am my sincere thanks to them. Thank you very much. If any questions, you can ask. Am I audible?
The participants can unmute themselves and ask any questions if they have.
Actually, I feel two things are missing. One is the, all faculty, of course, you people know that there is no eye contact. So I don't know how many of them, how many of you have followed my this thing. I'm not able to get the feedback, but I think hopefully the message has reached.
Yes, sir, I think so. Sir, any questions, you can reach Dr. Satish on ResearchGate, Dr. Satish VL. So with this, we conclude the talk, and I sincerely thank Dr. Satish on behalf of Aeronautical Department.
Madam, you are not audible.
Hello?
Yeah, it's okay now.
Yeah. I sincerely thank Dr. Satish for taking out his time and
Yeah, actually,
coming
yeah,
here.
yeah, actually, yes, I was little held up with the aircraft program. The meeting with Hamza here,
Yes, sir.
so that's why I could not maintain. I mean, come up, log in on time. So my sincere apologies for that.
I know, like scientists at NAL, you're very busy with it, but still you have taken out time for the session, and we are very happy for it. And promptly the response and all. I think uh, faculty who could not log in now could make use of the YouTube sessions as well, sir.